So in the last chapter, chapter 1, we got a really just a brief overlook of a couple of topics that'll lead us into actually looking into kinematics and quantifying motion. So we ended with taking a look at vectors, and that's not where we're gonna start in the next section. But we're gonna start talking and looking back at the concept of motion and using some of the things we learned in chapter 1 to apply right now. There is a pre-lecture video you should watch. It's a great way to start the unit or start the chapter by taking a look at a couple demonstrations, and I'll be doing a couple demonstrations in class. So we're going to start by taking a very analytical approach to describing motion. And we kind of did this already in chapter 1, where we talked about putting numbers on nature. So this is very similar to that. So in chapter 1, we talked about putting numbers on nature. And one of the big things we did is we assigned a 0 point, and we said, going to the right, we'll call that the positive direction, and going to the left, we'll call that the negative direction. And that's pretty much where we're starting off now, but now we're gonna expand on that just a little bit. So this is the on the board stuff again, kind of laying out what we're doing. Ranking task day 8, you should have watched that video already. We're talking about describing motion in this first section, and we're going to get into actual uniform motion and what that means, as well as our first couple equations in the second session. The key takeaways, which again, this is the stuff that if you can read this without lying, you're good. You can explain what uniform motion is and quantify with appropriate equations, or demonstrate with appropriate graphs, position and velocity versus time graphs. And we'll talk about those in the next section. A couple key formulas. The first two come from graphs, and we'll use graphs pretty interchangeably with equations because they tell us a lot of the same stuff. But first, velocity is the slope of position versus time, and displacement is area under the curve of velocity versus time. And then we also get our first two equations, which we'll talk about in the second section today. And the strategies we're going to be using are graphical, so using position, velocity, acceleration versus time graphs, and mathematical, which is going to be using the actual kinematic equations, which we talked about right here. And your homework, once this is all complete, you should be through problem number 35 in your problems packet. All right, so we got to first break this down, and this should be very, very intuitive for you. We're going to use X and Y axes to help us describe what's going on in nature so that we can put numbers on it, just like we did back in chapter 1. So we're going to use an X-axis to analyze horizontal motion and motion on a ramp, and we'll talk about that more later on in this chapter. And we'll use the Y-axis to analyze vertical motion, with positive being up, positive Y, and negative Y being down. And if you think about that, that means that if I were to draw this is my two axes, positive X, positive Y, negative Y, and in the middle we have our 0 point. And that should be very intuitive for you because that's what we always do in math class anyway. So sometimes, though, we can actually change which end is positive to make our problem solving easier, and we'll talk about that more later on. And again, so here's an example. So here is, we have a particle model. And this particle model can help us actually bridge the gap between watching physical motion and making a graph, just like we did with Lab 1.1. So we can also represent motion using a graph. The following pictures, this particle model, represent a student walking to school. So maybe they started walking to school. This is being taken one frame every minute. So 1 minute, 0 where they started, 1 minute, 2 minutes, 3 minutes. So maybe at this point, they're walking to school, and at this 3-minute point, they stop and they're texting on their phone, and they're all of a sudden then they see what time it is, and they're like, oh crap, I gotta walk faster. So the next couple minutes they're walking faster to get to school. Well, that puts up this nice little graph right here. And this graph this is the first chunk of their motion, this is that second chunk of their motion, and this is that third chunk of their motion. And we see, based on the position as a function of time, so this is their position at 1 minute, and this is their position at 2 minutes, and this is their position at 8 minutes, right? So every single instantaneous spot or time has some position associated with it, and we can use that to help us understand and quantify what's going on. So this is a nice bridge of taking this particle model or seeing motion and getting it to the first step of us analyzing it, which is making a graph out of it. And we did this already with Lab 1.1. Now, from position versus time graphs, I can get velocity. And here's why. We already talked about velocity. We know that the velocity is our change in position over time. Well, from a position versus time graph, that corresponds with a slope, because my rise is my change in position and my run is my change in time. So the slope of a position versus time graph will tell us an object's velocity. A steeper slope will correspond with a faster velocity. So here, this was in the middle. This is where our particle model, the dots were really close together. This is a steeper slope. This was at the end. This is when they started moving faster and our dots were further away from each other. So you can take your position versus time graph and make a velocity versus time graph. Again, just velocity is showing how fast you're moving. And you can do that by grabbing the slopes and plotting the slopes. So right here, this first section, the slope is 1. Here, it's a little less than a half, or 0.5. Here it's a little bit more than 1.5. So we can associate these different slopes. Again, we're just taking the slope because we know that the slope is velocity, and then we're making a velocity versus time graph. And that's a different way to represent the object's motion. So when you look at a velocity versus time graph, you are looking at how fast an object is moving. You don't know where they are, but you know how fast they're moving. Versus a position versus time graph, you see where they are, and you can look at the slope to see how fast they're moving. So I have a question for you. Here's a motion diagram of a car moving moving along a straight road. Here I have this 0 point right here. And which velocity versus time graph matches the motion diagram? Well, here it's moving one velocity, and here it's moving a faster velocity. So C is my correct answer. Again, velocity versus time graph shows me how fast I'm moving. So when does the origin matter? It doesn't. If I were to graph a position versus time graph from this, I would actually be starting, if this was a position versus time graph, I would be starting in the negative. And again, I'm going slow and negative and faster and positive. Okay, so this would be my position versus time graph, but my velocity versus time graph just uses the slope, to get velocity. Here's another quick check. Again, now we're going to the left. And if I'm wondering when the origin matters, now it helps me determine that the velocity is negative. And why is it negative? Because it's going in a negative direction. Technically, at every time interval, it has a negative displacement over time. So which graph is correct? Well, it's moving slow, and then it's moving fast as it heads towards 0. And D is the correct answer, because you got to remember, the further away I get from 0, the faster I'm moving. So right here I'm moving slow and towards 0. Here I'm moving fast and towards 0. So that's the velocity versus time graph for this object. Here's another quick check. This is a position versus time graph. What about velocity versus time? Well, for this first couple seconds here, their position does not change. Therefore, their velocity does not change. So we either have B, C, or D. Now, I am headed towards, let's maybe center court is our 0 point, and I'm headed towards the origin and then in the negative direction. So C is the correct answer, because for this second chunk, again, I have a negative displacement. Therefore, I have to have a negative velocity. All right, so let's do an example problem. And the following figure represents a position versus time graph for a car. And our first step is to draw the car's velocity versus time graph. And if this is a position versus time graph, I get velocity versus time from the slope. So I need the slope of each of these chunks. Well, the one in the middle is really easy. This slope equals 0. What about the first chunk? Well, my slope is my rise over my run. In this case, I have a negative slope, which makes sense because it's going in the negative direction. So my rise is -4, and my run is 2, and this is in meters per second, so I get -2 meters per second. So the first 2 seconds, so if I were to make a velocity versus time graph, the first 2 seconds has -2 meters per second. The next 2 seconds has 0 meters per second. And what about the last 2 seconds? Well, I go from -4 all the way up to 6. So my slope is 10 over 2. So I'm all the way up to 5. So I got to go all the way up here to 5 meters per second. And that is my velocity versus time graph. I'm going -2 meters per second for 2 seconds, 0 meters per second for 2 seconds, and 5 meters per second for 2 seconds. So maybe this is you backed out of the driveway, you put the car in park, and you headed off to school, right? So we can use these position versus time graphs to make velocity versus time graphs and help explain the motion that's going on. So here is the actual, better looking than what I just did, velocity versus time graph. And here's our quick little explanation. All right, we can also go backwards. We can also use the position versus time from the graph of velocity versus time. And the key thing is that's mostly. And calculus people get this really quite easily, but we'll explain it more in just a second. So the sign of velocity tells us the slope, explains the slope of position. Oops, we're going the other way though. The sign of velocity explains the slope of position. So here I have this nice positive velocity, therefore I have to have a positive slope. Here I have a negative velocity, so I have to have a negative slope. And that'll help explain what's going on with the position versus time graph. So the magnitude of the velocity tells us the magnitude of the slope for the position versus time graph. Now here's an important point. This graph right here starts at 0, 0, assuming that it starts at the 0 position. Now, I could argue that I don't know where this car started unless it explicitly states that it starts at 0, 0. So this graph is correct. The shape of this graph is correct. The shape of this graph is correct. But it could be moved higher or it could be moved lower, and it could start negative, whatever, it doesn't matter. The shape of the graph is correct. I don't actually know where the starting point is. We only know the general shape. And calculus people are really good with this because they know that this is technically an indefinite integral. So they don't know the constant, and the constant would be the initial starting position. So we can use velocity versus time to make position versus time graphs, but if I don't know where I'm starting, I don't necessarily know where I am. All right, so here we got a couple more quick checks. Here's a motion diagram of a car. Here's the position versus time graph, right? Here's my 0 point. That we're just plotting these data points. Here we have a velocity versus time graph, and again, this velocity versus time, it's positive velocity, therefore I must have a positive slope. 0 velocity, 0 slope. So the velocity versus time explains the slope of position versus time. And finally, which velocity versus time graph goes with this position versus time graph? Well, this one's a little tricky because for the first split second, it seems like it's going at a constant velocity. So my slope is positive, which means I have to have a positive velocity. Now right here to here-ish, my slope, it's positive. It's a positive slope, but it's decreasing. So on the velocity versus time graph, I see a decreasing slope, and then at the way end, my slope is 0, so my velocity is 0. Now, this little chunk in the middle, this has to have acceleration. And we'll talk about that later on in this chapter. So now that we understand our coordinate system and how we're going to make or take these position versus time graphs to make velocity versus time graphs, we can start talking about our first branch of kinematics, which is uniform motion. And I want to define this before we get into it. So uniform motion. What I'm going to define uniform motion as is constant velocity. Constant velocity. Otherwise known as there's no acceleration. Okay, so there's no acceleration. We will deal with what I like to call non-uniform motion, and that's going to have acceleration. But in this class, all we're really going to worry about is constant acceleration. Okay, so we're not going to get too much more in depth than that. There's a couple times throughout the second semester that we might deal with something a little bit more complex, but we're not going to worry about that right now. So we're going to break our physics of kinematics, the quantification of motion, into two sections. Uniform motion, which is constant velocity, non-uniform motion, which is constant acceleration. So we're going to start with the easiest one, which is going to be uniform motion. So in uniform motion, and we talked about this with the lab 1.1, the introduction to graphing motion introduction, the dune buggy was a perfect example of uniform motion. If I were to make a particle model of it, of the velocity versus time, or I could replace this with a position versus time, they're going to look exactly the same, right? It's moving at a constant speed, so every second it's covering the same amount of distance. For better or worse, it's pretty close. Now, when I graph that on a position versus time graph, every time interval, as time goes on, the rise, which is the change in position, otherwise known as the displacement, is constant. So there's a constant displacement in every time interval. This doesn't change. Well, we know that this is the slope of this is the velocity versus time graph, which means I have to have constant velocity. So uniform motion, constant velocity. It means that it's not speeding up or slowing down. It means that an object's motion has a linear position versus time graph. And we have equal displacements every time interval. Okay, so that's constant velocity, otherwise known as uniform motion. Now, there are a couple of equations that I can get from this. Graphically, we know that velocity is the slope, which is delta x over delta t. We could break x down into xf and xi. We could also break t down into tf and ti, but normally we just focus on this concept, which is known as the time interval. We don't worry about ti and tf, we just say how much time has gone by. So if I solve for xf, I get my first equation. Xf equals xi plus vx delta t. So this means that my final position equals my initial position plus velocity times time, how fast I'm moving and how long I'm moving. So let me give you an example of how we would use this equation. I started 5 miles from my house. I continued away from my house 10 miles an hour for 1 hour. So I started 5 miles away from my house, and I continued to go away from my house 5 miles an hour for 1 hour. How far am I from my house? 10 miles. Okay, 5 miles away was my initial position. My velocity was 5 miles an hour. My time was 1 hour. So I went an additional 5 miles. 5 plus 5 equals I'm 10 miles away. Okay, so it's a very easy concept. Now, this is the displacement. And this we can get from the area under the curve, or we can just say that the displacement, delta x, is proportional to the time interval. So what if I don't break down xf and xi? And here's my question. I'm going 65 miles an hour that's my velocity, for 2 hours. Okay, that's my time. How far away am I? Well, I am 130 miles away. Question, where am I? And the answer is, we don't know. That's a terrible question mark. That was just as bad. We don't know because this is just how far we've gone. It is not where we are. I don't know where I am, but I know how far I've gone. This one, I know exactly where I am. Okay, so slightly different equations. So here's the position graph of an object. What's my velocity at 1.5 seconds? I go to 1.5 and I say, okay, what's the slope of that line right there? Velocity is my displacement over time. Okay, so it's the slope at that point, which is going to be 20 meters, and it takes me 2 seconds to go that. Or does it? I said 2 seconds right here, right? And some of you might have agreed with me. Well, the first second, we're standing still. So my slope is my rise over my run. Well, my run is only 1 second, okay? So my velocity is 20 meters per second. All right, so let's go into an example problem. And it says a train is moving due west at a constant speed. A passenger notes that it takes 10 minutes to travel 12 kilometers. How long will it take the train to travel 60 kilometers? And there's a couple different ways that we can solve this. This is super easy because it is uniform motion. So uniform motion means that it's going to have constant displacement in every time interval. So if it travels 12 kilometers in 10 minutes, how long is it going to take to travel 60 kilometers? Well, that's 5 times this distance. So it's going to take 5 times the time because that's uniform motion. It is constant velocity. It's got constant displacement in every time interval. So we can do this a couple different ways. We know that delta x is going to be 12 kilometers. And if we set up a proportion, it's 5 times the distance. So it needs to be 5 times the time. Nice and easy. Another example problem. The soccer player is 15 meters from her opponent's goal. She kicks the ball hard. After half a second, it flies past a defender who stands 5 meters away and continues towards the goal. How much time does the goalie have to move into position to block the kick? So again, this is super easy because this is uniform motion. And some of you are easier or probably better off like having jumped into the problems because maybe throwing some of those graphs in there might have confused you a little bit. But it's important to know what's going on with those too because that'll help us understand the non-uniform motion better. But if we're 15 meters away and it takes a half a second to go 5 meters, how much more time does it have? Well, it's got 10 more meters, so it's got another second. So the goalie total of 1.5 seconds. Now, the last thing we're going to take a look at, again, is the velocity versus time graphs. So here I have the velocity versus time. The displacement, again, displacement is delta x, is the area under the curve of a velocity versus time graph. And here we have this nice square or rectangle, whatever you want to call it. My area is going to be base times height. My base, and again, the area is delta x. My base is delta t. My height is v. And you might look at this and say delta x equals delta t times vx. Oh, wait, that's delta x is vx delta t. And we talked about that already, and you're absolutely correct. So you can use the area under the curve of the graph to also get displacement if we have a velocity versus time graph. So to recap, if I have a position versus time, so an x versus t, the slope is velocity. If I have v versus t, it describes slope of position, or area under the curve is displacement. So we can get a lot from these graphs that help us describe the motion, and we can make some formulas from that as well. Here's a quick check. Here's velocity versus time graph. What's my position at 4 seconds? Well, if I go to 4 seconds, that's right here. Well, this is a velocity versus time graph, so it's not 0. If it was a position versus time graph, it would be 0. But what I need is the area under the curve, because that would give me my displacement. So for the first 2 seconds, it's the area under the curve, which is 4 times 2, which is 8 meters. And then the second 2 seconds, it's 1/2 base times height, so 1/2 4 times 2. Well, that's 4 meters. So my total displacement is 12 meters. So that's all we're going to tackle for today. We are going to continue this by getting into some more complicated things. Like now that we have this nice basis, we can start worrying about better describing velocity, and we'll do that in our next section, as well as getting into our next topic, which will be what happens if that velocity is changing, like it is right here, and that'll be acceleration. So we'll be covering those two things coming up. But right now we just have a couple easy steps, right? We have xf equals xi plus vi delta t, or we have delta x equals vx delta t, and we can use graphs to help show and explain everything that's going on. So we'll take a look at a little bit more about velocity and acceleration in the next segment.